In this video, I want to go over some formulas associated with conic sections. So if you have a pen and paper, feel free to take down some notes. So let's start with the first one, the circle. So let's say we have a circle with radius r, and the center has the coordinates h, k. The standard form of the circle, the equation, is x minus h squared plus y minus k squared is equal to r squared. So in order to write the equation of a circle, you need the coordinates of the center and the radius r. Now, some other things you may want to know is that the eccentricity of a circle is 0. The area of a circle is pi r squared. The circumference is 2 pi r. And the diameter is 2 times the radius. Now, in other less common situations, you may need to know the domain and range of a circle, given its equation. So the domain for a circle is going to be h minus r, comma, h plus r. So all you need is the coordinates of the center and the radius, and you could find the domain of the circle. Now, the range is going to be k minus r, and it's going to go up to k plus r. Now, from the equation of a circle, you can get the equation of a semicircle. So let's say if you were to solve for y. In this equation, solving for y, you'll get this. Y is equal to the square root of r squared minus x minus h squared plus k. Now, when you take the square root, you can get the positive answer and you can get the negative answer. If you just have the positive sign, you'll get a semicircle that is going to be the upper half of the circle. The negative sign, if you put that in front, you'll get the other part of the circle, the lower half. Now, of course, the semicircle, like the circle, can be shifted up, down, left, right by the values of h and k. So it can be in various quadrants. Now, if you solve for x, you'll get x. I'm going to need to get more space here, so let's clear this away. From the circle equation, if you solve for x, you'll get this. X is equal to the square root of r squared minus y minus k squared plus h. And like the other one, it can be positive or negative. When x is positive, you're going to get the semicircle on the right side. When x is negative, you'll get the semicircle, which is the left side of the circle. So you can get 4 different semicircles with those 4 equations. And for those of you who want a printout of these equations, including the domain and range of the semicircle, feel free to check out the links in the description section below. I'm going to have a printout with the graphs and the corresponding equations as well. So now let's move on to the next conic section, and that is the ellipse. So with the ellipse, there's 2 versions you need to be familiar with. So there's this one, where the major axis is horizontal, and here's the other form, where the major axis is vertical. So this is A, this is negative A, this is going to be B, and negative B. The length of the major axis, you could see in this case, which is the width, it's 2A. The length of the minor axis is going to be 2B, and that's the height for that ellipse. Now for the one on the right, this is negative a, this is a. A is bigger than b for the ellipse, by the way. The length of the major axis is still 2a, but it's no longer the width this time. For this ellipse, it's the height. The length of the minor axis, which is the width now, is 2b. So the length of the major axis is always 2a, and the length of the minor axis is always 2b. It's just the width and the height might be different. So this is the width. In this case, it's 2a. Here, the width is 2b. Here, the height is 2b. Here, the height is 2a. But the length of the major axis is always 2a. Now, the equation for the ellipse on the left is going to be x minus h squared over a squared plus y minus k squared over b squared is equal to 1. So notice that a is associated with the x-axis for the ellipse on the left, so you want a squared to be under x. B is associated with the y-axis, so b squared will be under y. So knowing that will kind of help you to know which equation applies for which shape. For the one on the right, it's going to be x minus h squared, but notice that b is associated with the x-axis, so we're going to have b squared underneath this, and then plus y minus k squared over a squared, and this is going to equal 1. Now for both equations, here we have the Pythagorean relationship, which is c squared is equal to a squared minus b squared, as opposed to a squared plus b squared. So based on that equation, that tells you that a is larger than b and a is larger than c. So when you're trying to determine which one is a is going to be the bigger one, the bigger number. The center of the ellipse is going to be the same as the center of the circle. It's h comma k. Now to calculate the eccentricity of an ellipse, it's c over a. For a circle, we said that the eccentricity is 0 because the circle is perfect. It's like completely even and symmetrical. The ellipse is not completely even, as you could see. A and B are different. If A and B were the same, then the ellipse will basically be a circle. Now, for an ellipse, the eccentricity is less than 1, but it's greater than 0. So it's between 0 and 1. For a circle, it's 0. For a parabola, the eccentricity is 1. For a hyperbola, it's greater than 1. So think of hyper. Hyper means higher than or above. Now, C is going to be along the same axis as A. So this is going to be our C values. Actually, let me use the same color. So this is positive C, negative C. Here, C is going to be on the vertical axis with A. Now, C will help you to find the coordinates of the foci. So we have 2 focal points for an ellipse. For a circle, you really don't need to worry about that. But here's how you can find the coordinates. It's going to be h plus or minus c comma k. So because c is along the x-axis, it's going to be here with h in the coordinates for the foci. Now, on the right side, the coordinates for the foci is h comma k plus or minus c. Now, the major vertices is h plus or minus a comma k. That's these 2 vertices here. Those are the major vertices. On the right, it's going to be h comma k plus or minus a. So that's these, no, that is these 2 here. Now, if you need to find the coordinates of the minor vertices, let's put VM for minor vertices. It's going to be h comma k plus or minus b. So using a different color, that would indicate these two. And for the graph on the right, it's h plus or minus b comma k. Which is the vertices here. Now, if you want the other formulas like the domain, the range, the x and y intercepts, you can find that in the formula sheet. Now let's talk about the area of an ellipse. So here we have a circle, and here we have an ellipse. For the circle, we have the radius r and r. For the ellipse, this can be a and this is b. Now the area of a circle, it's pi r squared. Basically it's pi times r times r. The area of an ellipse is very similar. Instead of r times r, it's pi times a times b. So you can see the similarities there. The circumference of a circle is basically 2 pi r. You could think of it as pi times r plus r. R plus r will give you 2r. You can approximate the circumference using this formula for an ellipse. Pi a plus b. Very similar to r plus r, but a plus b. This is actually like the least accurate of the circumference equations for an ellipse, but it's still pretty close. You may get like 98 or 97% of the true answer. Now there's some other formulas where you can get a more accurate answer for calculating the circumference. This one is longer, but it'll give you a more accurate result. It's 2 pi square root a squared plus b squared over 2 plus pi ab over 2. So this equation basically, it averages this form, which is what we have here, and basically the root mean square form. And it does lead to a more accurate answer of the true circumference value. If you want to find the exact answer, you need to use calculus, but this equation will give you an answer that's very close to the exact answer. But I'm going to put all those formulas in the formula sheet, including the calculus version. Now let's move on to the next conic section, the hyperbola. So on the left, we're going to have a hyperbola with a horizontal transverse axis. So it's going to open left and right. And on the right, we're going to have a hyperbola with a vertical transverse axis. So it's going to open up and down. So these points here represent the vertices. We have 2 vertex, and the coordinates of the vertices, well, we'll talk about how to get that soon, but the center of the hyperbola is h comma k, which in this case is going to be right in the middle. Now the equation for the hyperbola on the left, it's x minus h squared over a squared minus y minus k squared over b squared is equal to 1. So the difference between the ellipse and the hyperbola is that the ellipse will have a negative sign. I take that back. The ellipse will have a positive sign, but the hyperbola will have a negative sign. So that is a big distinction between them. The second distinction is the Pythagorean relationship. For a hyperbola, we have the equation c squared is equal to a squared plus b squared. For an ellipse, this is minus. So for an ellipse, a was greater than c, but for hyperbola, c is going to be greater than a. So this here is a. the distance between the center and one of the vertex. And the focal point is going to be where the hyperbola opens up towards. The distance between the center and the focal point, that distance is C. As you can see, C is larger than A. Now we know that the eccentricity of a hyperbola, you can calculate it the same way as an ellipse. It's C over A. So because C is larger than A, the eccentricity of a hyperbola is going to be larger than 1. For an ellipse, it's less than 1 because C is less than A. But for hyperbola, C is greater than A, so E is greater than 1. Now, for the hyperbola on the right, we're going to have the formula y minus k squared over a squared minus x minus h squared over b squared is equal to 1. Now, for an ellipse, A is always larger than B, and that's how you would distinguish A from B for an ellipse. For an hyperbola, A is not always larger than B. Sometimes A is larger, sometimes it's smaller, but how you identify A is always going to be associated with the positive term. B is associated with the negative term. That's how you distinguish A from B for a hyperbola. Now, if you want to find the coordinates of the two focal points, here it is. It's going to be h plus or minus c comma k. Notice that c is associated with the x-axis, so it's going to be associated with h. You got to add c and subtract c from h. For the hyperbola on the right, we need to add and subtract c from k. So this is going to be a, and this will be c. And here will be the focal point that C will lead us to. So starting from the center, we need to add plus or minus C to K to get the two focal points. Now, to get the vertices, which would be these 2 points, we need to add and subtract A from H, or from the center. Here we need to add and subtract A from the center, but along the y-axis, so from K. So this is going to be H comma K plus or minus A, and that will give us this vertex and the other vertex as well. So that's how we can find the vertices of the hyperbola. Now, the equation of the asymptotes, it's going to be y minus k is equal to plus or minus b over a times x minus h. For the one on the right, the slope is going to be inverted. So instead of plus or minus b over a, it's plus or minus a over b. But everything else will be the same. The plus or minus tells us that we have two asymptotes. This will be, let me draw that again. So this here will be the positive asymptote. That is the one with the positive slope. And this one will be the one with the negative slope. And the same is true for this hyperbola. Now, for those of you who want examples of how to graph hyperbolas, ellipses, and parabolas, I'm going to be posting a list of videos in the description section below. So once you look at those videos, you can see how to put some of these formulas into practice and how to use them. If you want to find the x-intercept for this ellipse, it's going to be plus or minus a over b. The plus or minus tells you that you can have potentially up to two intercepts. So plus or minus a over b, square root k squared plus b squared plus h. For the one on the right, if you want to find the x-intercepts, it's plus or minus b over a square root k squared minus a squared plus h. And this is all in the formula sheet, including the y-intercepts and the domain and range. But real quick, for this hyperbola on the left, the range is always all real numbers. The domain for the hyperbola on the right, it's all real numbers. Now let's move on to the parabola. So here we have a parabola that opens to the right. And over here, we'll have a vertical parabola that opens upward. So for this equation, it's going to be y minus k squared is equal to 4p times x minus h. Now the vertex of the parabola, instead of the center, the coordinates is going to be h comma k, and that's true for the other one as well. The eccentricity of a parabola is 1. Now on the right, the equation is going to be x minus h squared is equal to 4p times y minus k. Now what helps me to remember these two formulas, I think of this one as y is equal to x squared, and we know that's a parabola that opens either up or down. Here this is x is equal to y squared, and that opens left or right. What determines the direction in which they open is the sign of p. When p is positive, for this equation, it will open to the right. When p is negative, it will open to the left. For the equation on the right, when p is positive, it opens upward. If p is negative, it will open downward. The focal point, or the focus, it's always going to be in the direction where the parabola opens towards. So this is the focus, and this will be the focus as well. Now for a parabola, the focus is going to be p units away from the vertex. So to find the coordinates of the focus is going to be, for this one, it's h plus p comma k. So we traveled p units from the vertex to get to the focus, but we moved along the x-axis, so we add p to h. For the one on the right, we're going to add p to k, so it's h comma k plus p. Now this distance between the focus and the curve, that's equal to 2p, and this part here is 2p. So there's something called the lattice rectum, which is this distance here, and it's equal to 4p. If you need to find the coordinates of the lattice rectum, that's going to be in the formula sheet, so you can look that up for those of you who might be interested in that. But let's just call the lattice rectum LR. Just know that it's equal to 4p. So whatever this value is, that is the lattice rectum. And the same is true here. This is 2p, and this part is 2p. So if you know the value of p, you can determine the focal point, and you could determine 2 points on the curve, which will help you to graph it. Now the next thing you need to know is the directrix. The directrix is p units away on the other side of the parabola. It's p units away from the vertex. So because this one is vertical, the equation for the directrix will be x is equal to h minus p. So starting from the vertex, we traveled p units to the left. Now for a parabola that opens up or down, the directrix will be horizontal. The equation for the directrix is y is equal to k minus p. Now let's talk about the axis of symmetry. So if you have a parabola that opens to the right or to the left, the axis of symmetry, it passes through the vertex, and we know the vertex is h comma k. So because it's horizontal, it's going to equal the y coordinate of the vertex. So the AOS, axis of symmetry, is y is equal to k. Now for a parabola that opens up or down, the axis of symmetry is going to be vertical. It still passes through the vertex, and so it's going to be the x coordinate of that vertex. So it's x is equal to h. Now the x-intercept for a parabola that opens to the right or to the left is equal to k squared over 4p plus h. For the one that opens up or down, its x is equal to plus or minus, so there's potentially two of them, square root negative 4pk plus h. By the way, notice that when it opens to the right or to the left, you can only have one x-intercept. So here will be an example. Let's say if it looked like this, it's only going to touch the x-axis once. So that's why we don't have plus or minus. We just have one x-intercept. Whereas if it opens up or down, you can have a parabola that looks like this. And notice that potentially it can touch the x-axis at 2 points. So thus you have plus or minus. And the same is true for the y-intercepts. But you could find those equations in the formula sheet. So that's it for this video. Hopefully it gave you a good introduction into conic sections and some of the formulas that you need in order to graph them and answer questions associated with them. So thanks for watching.